When youth experience the negative effects of digital technology, the immediate reflex from public health officials and policymakers is almost always the same: mandate schools to reduce total screen time. To see if that actually works, researchers aggregated a decade of data from global school-based interventions, spanning from 2013 to 2023. This diagram shows the screening process. Researchers started with an initial pool of over 4,500 published records. By aggressively filtering for empirical validity and strict control groups, they whittled that mountain of data down to a bedrock of just 34 rigorous studies. These studies evaluated both children and adolescents, covering participants from 6 to 19 years old. What emerges from this data is a paradox in how school-based interventions actually perform. School programs are highly effective at treating the pathology of digital addiction, but they are entirely powerless to reduce the actual hours students spend on screens. The default public health metric, universal screen time reduction, fails the empirical test. We have to decode the data to understand exactly why. The meta-analysis tracked two distinct outcomes. The first was problematic digital technology use. This measures actual addiction symptoms, like compulsive behavior, loss of control, and withdrawal. To measure the success of the interventions, researchers used a standardized mean difference, commonly known as Cohen's d. In behavioral science, an effect size of 0.2 is considered small, 0.5 is medium, and 0.8 is categorized as a large effect. This forest plot visualizes the results for interventions targeting problematic use. At the bottom, the summary diamond reveals an aggregate effect size of 1.47, nearly double the threshold for a large impact. Yet individual rows show extreme variance, hitting outliers as high as 4.67. A heterogeneity score of 98.5% indicates that these variations represent real-world differences in program design and execution, rather than random sampling error. The aggregate data clearly confirms that school-based programs are capable of reducing the clinical symptoms of digital addiction. The second outcome measured by the meta-analysis tells a completely different story. This is raw screen time volume, the actual number of hours spent on devices. This is the forest plot for interventions attempting to decrease raw screen time. The summary calculation here drops to just 0.15. While that number is technically statistically significant, it is clinically negligible. It fails to translate into any meaningful real-world reduction in device usage. To test the robustness of this already weak finding, the researchers conducted a sensitivity analysis. This chart shows the overall average when individual studies are sequentially removed. They identified one massive outlier, the 2018 Yang and Kim study. Removing it collapses the initial effect size estimate to its bedrock of 0.15, confirming the broader failure of these interventions. The researchers suggest this failure is driven by factors schools cannot reach. First, family dynamics. Second, peer influence and broader social norms. Because screen time is resistant to change and deeply integrated into lifestyle and social expectations, school-based programming alone fails to overcome these external habits. Let's return to that staggering 1.47 effect size for problematic use. We have to ask a critical, skeptical question. Is it too good to be true? In scientific research, studies with small or negative results are often quietly abandoned rather than published. This phenomenon, known as publication bias, artificially inflates the published averages. This funnel plot detects publication bias. The y-axis measures study precision. The x-axis tracks effect size. Ideally, points cluster symmetrically inside the white triangle. Instead, there's glaring asymmetry: a heavy cluster of high-effect studies on the right and 0 low-effect studies on the left. That empty space means small sample studies that failed to find high effect sizes are missing from the literature entirely. A statistical check called Egger's test confirms this gap. To account for this missing data, researchers apply a statistical adjustment known as the Peace model. Once adjusted for publication bias, the true effect size drops from 1.47 down to 0.69. While the headline number was inflated, a bedrock effect size of 0.69 remains a highly robust, clinically meaningful validation. Treating the behavior works. If the effect is real, what specific variables separate the highly successful programs from the failures? Researchers fractured the data by characteristics. Universal prevention yields moderate results, but interventions targeting at-risk youth double the efficacy to 2.04. Externally led programs significantly outperform those run by teachers, and interventions using established psychotherapy models vastly outperform generic curriculums. Finally, the active integration of parents into the therapy process provides the ultimate multiplier for success. Successful digital well-being is not achieved through generic school assemblies. It requires clinical, targeted, and externally led interventions. The meta-analysis reveals a sharp divergence. Schools have no measurable impact on digital volume, but they can significantly reduce digital pathology. Mandating universal digital detoxes or screen time reduction programs across an entire student body is a statistical dead end. Educational resources must be reallocated toward targeted harm reduction. To improve outcomes, schools must identify at-risk cohorts early, utilize external clinical specialists, and deploy formal therapeutic frameworks that involve parents. To solve the digital health crisis in schools, policymakers must stop fighting the hours and start treating the behavior.